Section 9.1.1, Properties of Radicals. A radical expression is any expression that contains a radical. An expression containing an nth root is in simplest radical form when three conditions are met. So we know that this kind of what we call a square root symbol in general is called a radical. And there are three requirements we have to have. I'll come back to the first one. The second two are actually easier to spot. No radicals contain fractions. You see I have a square root here of a fraction. Can't deal with that. Can't have that. That's not simplified. You can't have a fraction inside a radical for a final answer. Third one, no radicals appear in the denominator of a fraction. So you see right here I've got a radical in the denominator. That's no good. I'm going to have to learn ways to clean up both of those. First one is a little bit harder to see. The radicand is the number that's inside the radical, and it's not allowed to contain a perfect nth power other than 1. So since the index here is invisible, we know it's 2. This is a square root. We want to make sure there's no perfect second powers, no perfect squares that are factors of 108. However, we can quickly see that 108 is the same thing as 36 times 3. Extend that a little bit there. And 36 is a perfect square. So because of that, the square root of 108 is not completely simplified. It's not in simplest radical form. All right, so we're going to talk about the different ways to fix these and actually simplify the expressions. So here's just a quick list of perfect squares from 1 squared all the way up to 20 squared. The numbers on the right, you're going to want to start to be able to recognize them as perfect squares. I don't expect you to memorize all of them, but it would be reasonable to think that you've already got up through 12 squared memorized at least, and then at that point it's not too bad to learn the rest. It just may be helpful going forward for simplifying these problems. All right, so now let's take a look at the one of the properties called the product property of square roots. Basically, if we have a multiplication inside of a radical, square root of 9 times 5, we can split that up into a multiplication of two different radicals. And in this case, the example, square root of 9 is something we can simplify and make it just 3, and then we can attach the square root of 5 on the end. So let's see what that looks like here. The square root of 24, this is where we want to look for perfect square factors of 24, and it happens to be that 4 is one of them. So I can write this as 4 times 6, which means I can then split that up so it's the square root of 4 times the square root of 6. Now the square root of 4 can be simplified, it's just 2, and then the square root of 6 just kind of gets attached onto the end, and that's my answer there. That's actually a simplified version of the square root of 24. If I type them in my calculator, I'd get the same value for each, but that's what I end up with. All right, so now I look at negative square root of 80, and I want to get the greatest factor that it has that's a common perfect square other than 1. So 4 would work, but I can actually do one better than that. I can actually take 80 and make it 16 times 5. Now I'm going to keep the negative out in front. I'm going to take 80 and make it 16 times 5. And then that means I'm looking at negative square root of 16 times the square root of 5. And square root of 16 is just 4, so it's become a negative 4. That's a negative times 4. And then the square root of 5 gets tacked on the end. That again means multiplication. That's negative 4 times the square root of 5, and that's my final answer. So that takes care of the first issue that we mentioned in simplest radical form. It has to have no perfect square factors in the radicand. Okay, so now let's take a look at a couple of examples that involve variables. Definitely a little bit trickier here. First of all, what I might want to do is I might want to split this up and look at it as two separate problems. Look at it just as the square root of 49 and then the square root of x cubed. Now the square root of 49 works out perfectly. That's just a nice 7, so we're good there. Square root of x cubed, what I'm looking for there is I'm looking for pairs really, because my index is 2. So if I have 3 x's, let's kind of write this down here as a little thing here, And if I group two of them together, that means that I can take out one x, and the square root of x squared is just x. So I'm going to put an x out in the front of a radical here. This will make sense when you see a few more examples. So these kind of combine to just be this x that's outside. Then, inside the radical, I'm going to have this leftover x that can't escape. And that may not look like it, but that's actually going to be my final answer. 7 times x times the square root of x. That's really what I'm looking at there. Again, it gets a little bit easier when we see a few more examples. So let's take a look at another one. I'm going to take the square root of 75 n to the 5th and make it the square root of 75. The square root of n to the 5th. Let me fix that n there. Now 75, does it have any perfect square factors? It does. 25 and then 3 is really what's happening there. So I can kind of save myself a step. And then for the n's, I want to think about n. I get 5 of them. Now I'm looking, again, the index is 2, so I'm looking for pairs, groups of 2. That's one group of 2, that's another group of 2. And so what I'm really looking at here is this is going to give me an n. This is going to give me an n. And because this one is not paired up, this gives me a square root of n. Now, when I simplify this, I guess I didn't leave myself much room. I'll just slide this over. That's fine. The square root of 25 is 5. Square root of 3 just stays what it is. Now, this is n times n, so that's actually an n squared, and then a square root of n. Now, what I should do is I should actually take the two things that are outside of, whoops, sorry about that, two things that are outside of the parentheses, the 5 and the n squared, and put them together. And take the two things that are in parentheses, the 3 and the n, and put them together. And so my final answer here is actually going to be 5n squared and the square root of 3n. So I hope it makes a little bit more sense after seeing a couple more examples. And we'll do some practice in class. It should help. So another property is related to division. Just like multiplication worked, we can actually do division here. If you have a division, often shown by a fraction, of a radical is being applied to that fraction, you can split it up into two different problems. This is one way that we deal with the problem of having a fraction inside of our square root. So this first example, square root of 23 over 9, all I have to do there is simplify it by writing it as the square root of 23 over the square root of 9. And then I want to make sure that I don't have a radical in my denominator, but my denominator can be simplified. The square root of 9 is just 3. Now 23 is actually prime, so it actually doesn't simplify at all. I don't want to approximate it. I just want to leave it exactly like that, square root of 23 over 3. Let's do the same type of thing for the second problem up top. Negative square root of 17 over 100. I keep my negative, and I'm going to make it square root of 17 over the square root of 100. Get the square root there. Once again, I don't want to have a radical in my denominator, but it will simplify. And so I end up with negative square root of 17 over 10. And that fits the descriptions I had before. 17 is prime, so we're good to go. So that's going to be actually my final answer. All right, let's see just a couple of more examples involving some variables. Square root of 36 over z squared. I just rewrite that as the square root of 36 over the square root of z squared. And square root of 36 is just 6. Square root of z squared is just z. And that's just because, you're looking for a pair of z's to come out of the square root, and there's 2 of them for z squared, and there's nothing left to go inside, so that's what you get there, 6 over z. Same type of thing for the last one here. May have just a little bit more to do. Square root of 4x squared over the square root of 64. Now, for my numerator, I'm going to be thinking about that actually as the square root of 4 and the square root of x squared as 2 separate problems, whereas I keep my square root of 64 in my denominator. Square root of 4 is 2, square root of x squared is obviously x, and the square root of 64 is 8. And so my final answer would be, oh, wait a minute, hold on a second there. That's not going to be my final answer. I can reduce that. 2x over 8, I can reduce the 2 over 8 to make it 1/4. And I don't need to have that 1 anymore, so I can just maybe make it x over 4. And that'll be my final answer. There we go. That looks actually a little bit nicer. All right. I hope this is starting to get a little bit more clear. So one last thing to look at. Sometimes we would try to simplify individual radicals, but we actually would need to combine them first in order to get there. We can't simplify the square root of 5 or the square root of 10 any further, but we can combine them through multiplication here. We know that we are allowed to do this with multiplication, and we see that that becomes the square root of 50. Now, the square root of 50, 50 has a perfect square factor of 25. And so the square root of 50 is really the same thing as the square root of 25 times 2. And the square root of 25 is 5. So this was one where we actually couldn't do it without rewriting it first. Just a different way to think about it. Same type of thing for the fraction here. I may actually want to go back and put this in as a square root of one big fraction because 6/8 can be reduced. That can be reduced to by a factor of 2 to be 3/4. Then I can rewrite that by making it the square root of 3 over the square root of 4, and now my denominator will simplify nicely to just be 2. And so I get the square root of 3 over 2 is my final answer. And that's it. That's all that we have to work with. So I hope this makes sense.